So I just hour ago posted everything to GitHub, so the code is available, everything is there. The repository is called token ZK compression. There is a very brief README and the same presentation you can see here. And
Risto is now a Rust guru.
Yeah, me and my friend Claude and some Chinese fellows as well. So, and I have some demo files here as well, which are not related. So this is a kind of lightweight thing, actual demonstration, but the heavy lifting goes on in Rust SDK, which is in our repository. But the proving takes something like 10 minutes, so let's just start with it. So it's the same repository, same state right now. And just let's take a existing pre-generated token, and which is in demo directory. It has 2 transactions, and let's start it. Okay, so it takes a moment to compile and then starts running. And yeah, I have one demo token here, which has Unicity certificates on mint transaction and the first transfer transaction. And it takes a moment to build a project. So build has 2 targets. As we see, one target is RISC-V 32-bit. Another target is Apple Silicon, which runs the host application. So the compiling should be done in a second or 2. Okay, and we have validated the token, generated execution trace, and we have started proof generation. And while its proof generation is going on, let's get back to what we are doing. So motivation, Unicity token is a blockchain, and it grows linearly when we transact more with a single token. Every transaction adds a transaction to the data structure, and it makes the data structure bigger, and it also increases the recipient's validation effort. So to be completely trustless, he has to start validation from a Genesis or mint transaction. Then all transactions, we have a drawing. One token right now has a structure where there is a mint transaction and more transactions. And of course, all the transactions are connected cryptographically. So the transaction 1 refers to mint, transaction 2 refers to transaction 1, and so on. So it's actually like a blockchain. And our motivation why we need ZK-based compression is to obtain some constant size and constant verification effort for tokens. So instead of having many transactions here, we run the transactions through the ZK proof-based compression. The statement is that, yeah, I have verified those transactions and they are valid, and this is a cryptographic proof. And the cryptographic proof has like almost constant size. It doesn't matter how many transactions there are. And if it's a succinct scheme, then it also has like a much smaller validation effort compared to re-executing all the transactions and revalidating of them. So we do not care, of course, about zero knowledge here, because the transactions themselves are already private by using some simpler, more efficient cryptographic methods. Or another use case, we take the token, compress it, and we can return it back to the bridge contract on some other blockchain. Because if the JSON structure is kind of big, then the gas cost might be like too expensive if we return the bridged tokens to the origin blockchain. Or we can do task collection, or maybe it's too expensive for task collection. I don't know. So this is the idea why we do it. And tools, ZK VMs are booming, and it also seems that even Ethereum is speculating with switching to ZK VM, which is based on RISC-V architecture instead of having native ZK EVMs. And RISC-0 is the first one. SP1 followed. OpenVM is a bit more recent. They are kind of close to each other, but maybe we can say that they are like learning from like older ones. And basically all of the ZK VMs which are practical are based on RISC-V architecture. So there is one crazy one using Lisp as a programming language, but it's not really practical to use. And the principle, how it works. We write a program which validates a token, and we run it on this emulated RISC-V CPU. And the host machine who emulates this environment generates execution trace. And then the cryptographic algorithm to generate Stark proof takes a trace as an input and generates a succinct cryptographic proof that the transcript was executed according to some pre-specified rules or pre-specified algorithm. So first there is a commitment to a specific algorithm or program, and then whoever validates this proof also verifies that the proof is about executing some kind of program in correct way. And RISC-V is an open source CPU architecture. It's kind of simple. It's modular in its simplest form. It has only 32-bit arithmetics, addition, multiplication, shifts, but no complicated things like floating points and other stuff which are optional extensions, and they are not used in ZK VMs. But this ZK VM creates an abstraction layer on top of the so-called native field arithmetics, which the ZK proofs are operating on. So there is no direct access to actual variables which can be used as a native objects we run our mathematics on. So in order to overcome it, there are so-called coprocessors implemented for ZK VMs. So coprocessors, how they are connecting to this CPU, emulated CPU, look like an actual physical coprocessor. And what they do, they implement some low-level cryptographic operations mostly, like the compression function of SHA-2 hash function, or some field arithmetics for elliptic curve cryptography to make it faster, or something like this. And but still, if we execute our stuff natively on the low-level field of proof system, when it's still possible to run things in much faster way. But we lose this kind of flexibility in case of ZK VMs. So ZK, and almost without any formulas, what the ZK is. So it's a set of functions or algorithms. First we have a setup. We take a program and some parameters, and it generates proving key and verification key. Second program is actual proof generation. It takes the proving key, public inputs, and secret inputs. Public inputs is public information which are also available for verifier, but secret inputs are thrown away And if a ZK system provides zero knowledge, actual zero knowledge, then even no information about secret inputs leaks to the verifier or outside world. And the third algorithm is a verification algorithm, which takes a verification key, public inputs, and the proof generated during a previous step. And it either is happy or it's not happy about the proof. And the valid proof can be generated only if a program executes correctly without holding somewhere. So in our case, the program is a token validation code. Parameters are, for example, security parameters like how many bits of security or roughly what's the key length is. Then proving takes public inputs. The public inputs is a necessary data to connect our proof with its environment. For example, we connect the proof with mint transaction, or the public input is actual token ID and token class. And public input could be also how many transactions there are compressed into one proof. So the public input is like the thing what connects this ZK proof to outside world, to neighbors in this data structure in our case. And as we see, the secret inputs are not needed to validate the thing, so we achieve some compression. And yeah, if token is not valid, there is an invalid transaction, then it's not possible to generate the proof because our program rejects the token. And as a first step, we make a commitment to the program. So everybody who verifies knows that, yeah, the program is doing the right thing. It validates our token. Yeah, as said, that all practical ZK VMs execute RISC-V bytecode as an input. And basically, the only practical language to compile into this bytecode is Rust. So I think the RISC-0 is experimenting with C++ as well. And in theory, any LLVM language can be used, but it's only theory. We do not have like necessary tooling. And for this current demo, the biggest effort is in fact providing Rust state transition SDK. And it needed some modifications. For example, the verification code cannot have any references to random information sources because our verification program must be deterministic. And we also cannot use a standard library for efficiency, so that the Rust SDK has two compilation configurations, one with standard library, one without. And SHA-2 and elliptical cryptography can be accelerated. I have implemented SHA-2, but no signature validation. So likely the verification will be a bit faster with this implementation. And also, it's interesting that it's possible to use recursion. So the statement or our program can validate transactions, and it can also validate previous ZK proofs. Like there is an example here. So this one here, in fact, is a ZK proof and some extra transactions. And the final proof tells us that the previous ZK proof is valid and some extra transactions on top of it are also valid. And yeah, there is an illustration how it works. So that in fact, we can apply this ZK recursion many times for a single token. We just modify the data structure instead of individual transactions. It can be a ZK proof. It is connected with like previous and subsequent transactions using public inputs, which are basically hashes. And if we run a second time the proving, we can we achieve compression again. So we can do it again and again, and still the size of the token will be the same.
Risto, where are you proving things right now? Are you running on your machine?
In my laptop, yeah.
Okay. And how much time typically it takes to generate this current proof?
It's done. It's 900 seconds. Yeah, and then we see the public outputs which are printed out. So when we validate the proof, we know that so this is the hash of the algorithm, which is used as a trust anchor. And those are the public inputs, the public, no, input output doesn't matter, which connect with this generated proof with other tokens. So we have token ID, token type, example token, and last state hash, which is used to connect it to the following transactions. And regarding proof files, it's like really easy to switch to different ones. Right now, we use the fast proof file. It's possible to use succinct.
Very cool.
And so on. And if you're using Grot16, the proof size will be like 250 bytes. But this is better for bridging and scenarios.